So I would make my ux squared. I would make my substitution 1/2 du for x dx, so that I had 1/2 the integral from 0 to square root of pi, cosine u du.
Sorry, I was in
Now, this is where you have to make a choice. You have to either change your bounds, or you have to plug back in the x's at the end. So, how many of us like to change our bounds to start?
I like to change the thing.
Okay, so let's change our bounds. Let's get rid of the x bounds and change them to u's. So what that means is I need to find u of the square root of pi, and I need to find u of 0. So the square root of pi goes in for x, so you get the square root of pi squared. So my new bound becomes pi. Put in 0, 0 squared is 0. So my new bounds are from 0 to pi. We get 1/2. Antiderivative of cosine is? Very good. No, positive sign.
Oh, you said anti.
So you go from pi to 0. So you have 1/2 the sine of pi minus 1/2 the sine of 0. What is the sine of pi? Okay, what is the sine of 0? So our final answer is? Good? Not terrible?
So what happens to the du that's just there? It just goes away because we find the antiderivative.
Great. So anytime you find your antiderivative, then the du kind of gets encompassed back in.
Okay.
So we just have to make sure that these are du's to u's and
not
dx's to x's. Exactly. That's the whole big idea of substitution. So what would we make our u in this case?
Pi t.
Yep.
Pi t.
So what's our du? Pi dt. Do I have a pi anywhere in here?
Yeah.
No, inside the angle, not like hanging out.
Fancy parentheses.
So I gotta divide by pi. If you're gonna change your bounds, it would become u of 1/2 becomes 1/2 pi, and u of 1/6 would become 1/6 pi. So these bounds actually get a little uglier because we have to add in the pi, but that's okay. So let's do some substituting. We go from 1/6 pi to 1/2 pi. And we have cosecant u, cotangent u, du, and the 1/pi kind of pulled out in front. What is the antiderivative of cosecant u, cotangent u? Perfect. It's negative cosecant u. So you get negative cosecant u, evaluated from 1/2 pi to 1/6 pi. And then outside all of that is our 1/pi. Here's where you have to be kind of careful or mindful. So that 1/pi is out in front. You have negative cosecant of 1/2 pi. But that would be like minus a minus. So this is going to turn into a positive cosecant 1/6 pi. And then that 1/pi distributes to all of them. So cosecant is really what? It's 1/sine. Well, yeah, if you're taking your negative from the beginning. Yep. So if the sine of pi halves would be positive 1, and then because there's a negative out here, it'd be negative 1. And then you could distribute your 1 pi if you wanted. How about the sine of pi 6?
1/2.
It is.
And then over, or 1/1/2 is 2. So it's
1 over.
1.
Oh,
Right?
it's that answer.
Is 1.
Okay, I was
Sorry.
like, how did you go from 1/1/2? Yes. So that becomes
Over
1.
pi.
So you get 1/5. That's not a very pretty pi. Speaking of pi,
When's Pi Day? Yeah.
so
What?
yeah, my
March
due
14th.
date.
Yeah, that's the day to crush fries.
All right.
I'm excited. I'm so excited.
How about
You understand?
sine of pi or sine of theta over cosine squared theta? I actually think there was something similar to this.
Do you really need to find a U?
Yeah, you don't need
Wait, do I need one?
No.
What could you do to this problem?
You can turn it
Tangent.
into tangent
Tangent.
theta.
Tangent over cosine.
Theta.
Theta. Then multiply by sine.
It's
So if you
theta
do,
It's tan theta, secant theta.
so you get tan theta, secant theta. Yep.
Which
Now, what? Which is secant.
Yeah.
What if I told you you had to do it with a
Just
Just to make you think. Which one would you pick? If you had to make it a pi, if you had to make it a U.
Sine, cosine.
Because there are multiple choice questions where you don't solve them, but they change the bounds. So like they would say, by U substitution, what would this problem look like if we changed it from theta to U?
I'd say cosine theta.
So you're, okay, so let's say we make
Oh, I get it.
U cosine theta. That was per Jason's suggestion.
Oh my gosh,
super.
What's the derivative of cosine?
Negative sign.
Positive.
So what would that do to my integral?
Use U.
This would become U squared, so I made it U to the negative 2. du. We need that negative out in front to account for on the side. What's your antiderivative of that?
Wait, yeah, where's the sign? Isn't it on?
Sine of theta d theta went with the du.
Yeah. Oh, no way.
Yahweh.
Oh my god. Negative on the side. That was like skipping.
So, you add 1, so you get negative 1 over negative 1. What happens to your negatives? So now, this would transform to 1 over u. What was our u?
Cosine.
And what did you say if you had changed that to sines, the sine and cosines to tans and secants? Your answer was secant. What's 1 over cosine?
Secant.
So do you see how it actually still works, even if you change it to the u's and the bu's? Wow, we're supposed to evaluate from pi thirds to 0 though. So what's the secant?
Sine,
1/2 minus 1.
Jason, we're on the same level.
You get 1. Because remember, this is 1 over 1/2, because it's 1 over the cosine of 1/2. So it makes it 2. 2 minus 1 is 1. If only we could stay with the trig.
Oh, this is something. Oh, yeah. I knew there was something more.
So now we're going to look at the exponentials and the logs. How's easy to do?
Yeah, I want to go over this like a lot. Like easy house. Will you just have natural logs on these tests for now? Like, will we ever get like log questions? Like, actually just one.
Not for the most part. They typically stick to the E's and the LNs. Yeah.
Like that, yeah.
So we are going to integrate exponential functions. So just as a reminder that the antiderivative of e to the x becomes e to the x plus c. So that's just a reminder. The integral of the natural exponential function, we've talked about it before. The integral of e to the x dx becomes e to the x plus c. Yeah, it's not like on your paper because we did it before.
What about natural
We'll get there.
yeah.
So in the case of this problem, we have e to the 5x. So it's not just an x anymore. So this is where you have to use that u substitution to really say, okay, how do I account for that 5 being on the x? What's it going to do to my antiderivative? So what we're going to do is we're going to say, all right, the u is 5x. My du becomes 5 dx. Since there's no 5, I have to move that 5 over. So the dx becomes 1/5 du. So what does that 5 really do to your integral? It's going to add this 1/5 to it, right?
Yeah.
Because this now just becomes 1/5 the antiderivative of e to the u du. But we know the antiderivative of e to the u du is e to the u plus c. So the 1/5, or the 5 here, becomes that coefficient. So you get 1/5 e to the 5x plus c. Something like that's something you could probably memorize and not have to actually do the u substitution. But it's very nice to see why through u substitution that it is that derivative instead of just kind of giving you a reason to memorize it. Next example. Now I got e's and trig. What's my u? Yeah.
How does it make you substitution? Oh, within, without.
What's my du?
Negatives or something.
Derivative of sine is positive cosine.
Oh yeah, my bad. I
Yeah.
was thinking antiderivative.
Sometimes I just agree too. Like I'm always like, yeah, good job. No. Okay. So u is sine theta, du is cosine theta, d theta. So you can see directly here how this is going to become my du. So we get the integral of e to the u du, whose antiderivative is e to the u plus c. So we have e to the sine theta plus c. Not terribly hard.
Perfectly.
What?
It works out too perfectly.
It's like it's too nice.
Then the cosine is just
It's quiet.
Wait, I need to
Quiet.
I don't know what happened. So what happened to the cosine?
Things.
So like the cosine theta
Oh,
d theta
du.
became du.
Du over cosine. Okay.
Well, remember the u is going to be the exponential function value. So it's actually easier when you have the e's because like the decision's pretty much made for you.
So
Very much.
The one below it,
So well, what happens to this?
yeah. So you did u and over u, or no?
No,
That just
because
make it harder.
when you derive it, it'll be.
Great, you need to still get rid of the dx because the dx can't stay du. So what happens is this is the square root of x. What's the derivative of the square root of x? Exactly, because this becomes 1/2 x to the negative 1/2. So what's nice about this is it becomes 1 over the square root of x dx. So you can like substitute this out, but you have to make sure you remember to multiply by the 2. So since there isn't a 1/2 here, that 2 has to come with the du. So that's what happens sometimes. Like when you take your derivatives, you have these coefficients, and that's what we're bringing out as those constants. So you have 2 e to the u du. So you get 2.
No, she flipped it the other side. You have to multiply it by 2 to get rid of it on the one side. So, yeah.
Yeah.
Yeah, because I was thinking that too, and I'm like, oh, shoot.
Okay. So then you have 2e to the square root of x plus c. And sometimes I do make that error. Like you know what I mean? Like when I'm like, oh, 1/2 becomes 2 over there. Especially when you're on the board. It's sometimes super hard to back away and see your work. The e's aren't bad. It's the ln's that are stinky.
Oh, heck,
Oh.
here's
The
another.
ln's are a little harder to pick what you make your u. Like the e, that u is so set in stone as to what it has to be. And same with even like the trig stuff, you typically know it's the angles. The natural log ones,
So it's not going to be x or u? It's not going to be u?
the u is not going to be x, no.
Change it to
Is
e.
it worth it?
No,
Could
it's
be.
actually just the ln.
Oh.
Because the 1/3 is kind of like your constant. You don't really want to pay attention to it. So in this case, if you think about the natural log and what its derivative is, we want our u value to be the ln of x. Because the derivative of the ln of x is 1 over x dx. So now I can take this 1 over x dx from here.
I'll put it 3 1/3 outside.
Yep, and I can take the natural log of x here and replace it with the u. So I've gotten rid of the natural log and the 1 over x. What happens is that 1/3 just kind of becomes a constant out in front. So that I have u du. So when you have those constants or those numbers that are acting as coefficients, we bring them out. That's what makes integration kind of nice, that you have that rule where the k value can get brought out in front. So now what's the antiderivative of u?
1/2 u squared.
So you get 1/3 times 1/2 u squared plus c. So we get 1/6 u squared plus c, and then we just change our u back to natural log. The natural log is like the cosines and the sines. You'll see the squared written outside parentheses, and you can see it written like this. So your textbook will sometimes square it inside the parentheses like we do with sines and cosines. So again, just kind of understanding notation, that squared can move between the two. So what am I going to make my u? If I make it e to the x and I leave out the plus 1,
Plus 1, yeah.
try it. And then, what?
Yeah, do e to the x.
Why would I want to include the 1? What would be nice about including the 1 versus not including the 1?
Because when you try to like replace the dx with u, when you take the derivative, the 1 just goes away.
Exactly. So I need to include that u so that I get the 1, so I have e to the x plus 1 du becomes derivative of e to the x, which is derivative of 1, which is, so it kind of clears itself out. So now I get 1 over u du. Do you see how making it e to the x would have given me 1 over u plus 1? What's the antiderivative of 1 over u? U. ln of u. Remember, from here on out, we're playing it safe and putting our ln's with absolute values, because we don't necessarily want to have to account for the domain of e to the x plus 1. You could be wrong by putting the absolute values. You could be wrong by not putting them, though. Okay? How about the next example?
2x.
Okay? So the suggestion is to make 2x my u. Let's try it. So think backwards to what our rule was for a to the u in terms of derivatives.
I'm talking about the
Yeah, you're going to be. So, like, it is going to be a to the u over the ln of u. Because if you think about the derivative of it, it's a to the u times the ln, or times the natural log of a. So what we have to do is, if we had this, we'd have to cancel out that ln of a. So instead of having it multiplied by ln of a, which isn't happening, we have to divide by the ln of a. So yes, the antiderivative is 1/2, because that's your coefficient out in front, a to the u all over the natural log of u. Or, sorry, the natural log of a, which in this case is 5. Plug back in your u, and don't forget your c. That one looks like
Why natural log of 5?
So if you work it the other way, like if you think about the derivative of a to the u was always a to the u times the natural log of a times du. So back in the day, if y was equal to a of u, then dy dx is a to the u times the natural log of a times u prime. So what we did was we said, okay, let's work backwards. I don't have any of this in that problem right now. So my u is the 2x. My u prime would be 2. So here's the 1 over 2 to get rid of that to give you this. The natural log of 5 would eliminate this. So we just kind of worked it backwards. We said, okay, if this is what the derivative should look like, this is missing that, so that needs to be in my antiderivative. Yeah. Oops. The only thing new now is we have bounds. So all of those had plus c's, all of these have bounds. So, u value pi t du, I never like saying that, pi dt. If you want to change your bounds, you need u of 1 and u of 0. So instead of being from 0 to 1, we're from 0 to pi. So all that means is that when I get to this step, I can just plug in my pi and my 0 to my u. What is e to the 0?
1.
Yep. What do I have over here, though, that I didn't account for?
The pi.
This had to be 1 over pi. 1 over pi.
That's it, right?
Hmm?
That's it?
Mm-hmm. What's the next one? What's my u going to be?
Ln of t.
Very good. So derivative of the natural log of t becomes
1 over t.
change our bounds. Natural log of e becomes
1.
the natural log of 1 becomes
0.
So my new integral is from 0 to 1 of a u du. Antiderivative of u is? Yep. So we get a nice, pretty 1/2. It won't seem like such a simple answer for such a complicated looking problem to start. What's my u going to be in the next one?
X squared.
Bless you.
Thank you.
So remember, it doesn't matter that this x initially is written out here. Since multiplication is commutative, you could really think of this as being rearranged, which is how we're getting rid of that x dx with the du's. So I know sometimes like when the x is out in front, it sort of like trips us up. But again, multiplication is commutative. The x could be before or after the e to the x. Just for purposes of writing properly, we always put it out in front. You need u of 2 and u of -1. 2 squared is 4. 4 plus 1 is 5. -1 squared is 1. 1 plus 1 is 2. So we have 1/2 the integral from 2 to 5 of e to the u du. All right, that sort of puts us done with U substitution. Last year I made a handout.
How do we know the difference? Like looking at a problem, how do we know if we should use U substitution or just take a regular integral? Like,
So typically, you cannot integrate a function that would need the chain rule if it were like a derivative. So that's your hint, is to look for a function within a function. So like with the trigs, if it's not an x, or like something simple, if it would have been a chain rule for a derivative, then you use U substitution.
Wait, there is no chain rule for these?
This is like the chain rule. U substitution is the chain rule of integration.
Oh, this is the chain.
U substitution.
okay, so the composition of the problem is like the indicator.
Yes, like if you have composite functions.
Okay.
Basically, you could always use substitute. You just don't always have to use substitute. Like if you use substituted on a problem that didn't need it, it would still work. You would just get like du equals dx with nothing with it. So like if you did it and you didn't need U substitution, you'd get du equals dx. Or typically our du's equal something with a dx.
When are we testing on this?
Early next week.
Okay.
So that's kind of where my hesitation comes in now. We still have like 30 minutes of class. Your textbook does not have a lot of good E problems. So I have a handout for you. Maybe we'll just do those handouts.